Hey gang, so we're going to look at now another kind of hypothesis test with two samples. Again, we're talking about independent samples here, and we're going to be now testing claims about comparisons between two population proportions. This is the case. Again, we're going to have simple random samples, and they're going to be independent, so nothing about one sample affects anything about the other sample. Um, we also have to have large enough samples, and one way you can enforce large enough samples is that, remember when you're doing a proportion test, right? We want to test the proportion of people in a population that owns a cell phone, let's say. And so you'd go ask 100 people how many cell phones they own. One way to ensure the samples are large enough, we'll say that the number of successes and failures has to be greater than 5. So you'd have to have at least 5. Your sample's big enough if you have at least 5 people with a cell phone and at least 5 people without a cell phone. Anyways, those are the conditions. And so as before, the idea is we have two populations underlying the problem. I'm calling them X1 and X2. And we go out and sample these populations and compute a proportion, right? So if you went out and sampled a certain number of people from this proportion from this population and found, let's say the number of people you sampled was N1, and the number of people with whatever characteristic you were asking about, with cell phones or with red hair or whatever thing you're studying, we'll call that X1. This is the sample proportion, right? Which we can label as, I'm going to use the notation p hat, and we'll have 1. You can do the same thing with the other population, right? The number of successes and divided by the sample size, right? Where successes here is just whatever thing you're interested in, okay? Now, these are the sample proportions. There is a true proportion, right? We're hoping that, whenever you do this kind of thing, you hope that your sample proportion in some way approximates this. So what we're trying to compare is the actual proportion, P1 and P2. These are the two features we're trying to compare, but we don't have access to those proportions. But that's what we're trying to compare. So we'll form a null hypothesis and an alternative hypothesis about these proportions, right? Typically, our null hypothesis is that the proportions are equal, or put another way, that the difference between the proportions is 0. And the alternative hypothesis will be something like, let's see, what am I going to do in my example? In the example I'm going to give it that one proportion, that the sample proportion is greater than the other one, right? You could have less than as well. So just depending on what it is you're looking at. So that's the setup. You remember, kind of in the background, we're creating a new distribution from the differences in these sample proportions. In other words, a distribution formed by that computation, right? That you would take sample proportions, that you're taking the difference between sample proportions, right? And this distribution, we're going to have something called the pooled proportion that we're going to use when we compute our test statistic. I'm going to use the notation p bar for this. Sometimes it's called the common population proportion estimate. Oops, let me make that equal sign a little better. And this thing is computed by taking the two numbers of successes and dividing it by the sum of the sample sizes. It's as if they were one big sample, right? The two sample sizes together, and then the two number of successes together gives us the proportion of that whole group to hopefully estimate the population proportion, okay? This distribution, the distribution, let me move this. This distribution that I sometimes just call the I'm just using D to mean it's a difference distribution, will follow a normal distribution under the null hypothesis with a mean of 0 and a standard deviation computed by this using this p bar, 1 minus p bar, 1 over n1 plus 1 over n2. Okay. And so because we have this normal distribution, our test statistic is going to be a z-score. And we compute our z-score by taking the difference between these two sample proportions and subtracting the difference between the true population proportions. Typically, under the null hypothesis, this is going to be 0. Right? And then we divide this by our standard deviation. Okay, p bar, 1 minus p bar, 1 over n1 plus 1 over n2. Okay. Again, these formulas are a bit more complicated than the formulas we use when we only have a single population that we're testing. But it really isn't much more difficult. You just have to plug in a few more numbers. There are plenty of calculators online that will do it. You just need to give it the right values, right, for your particular problem. Or you can create one in a spreadsheet. That's what I've been doing to work through example problems. All right, let's do an example. There we go. So researchers believe that a certain illness is more prevalent among mice living in urban areas than mice living in woodland areas. So there's our two populations. The researchers sample 1,200 mice from urban areas and find 12 with the illness. And from woodland areas, they sample 1,000 mice and find 8 with the illness. We want to test the claim that the illness is more common in mice from urban areas than in mice from woodland areas with a 0.05 level of significance. All right, let's just start collecting our information, right? So let's call this, let's start with our null hypothesis, right? The null hypothesis is going to be that the population, I'm going to use U for urban. Let me not put a tail on it so we don't confuse it with mu. U for urban. Now it looks like a V to me. I'm going back to the tail. I'll just try to be careful. Urban, the proportion of urban mice with this illness versus the proportion of woodland mice, that those proportions are equal. That's our null hypothesis. So their difference is 0. Our alternative hypothesis is we said that it's more common in the mice from the urban areas. So if we take PU minus PW, we should get a positive number, right? Because PU should be greater, but the alternative hypothesis is that the PU is greater than PW. All right, now from our problem, let's get a few of the numbers we need. We want P hat for our urban mice, right? So just looking up here, right? The things that we're going to need for this formula, we're going to need these two P hat values, right? Which I give you the formula for those up here. And we're going to need P bar, which is formed right there. So those are the things we're going to need. And then we know P1 minus P2, in this case, is 0, right? That's coming from the null hypothesis, or in this case, PU minus PW. So, okay. So back to our values. P hat for the urban environment, that's going to be the number of successes divided by the sample size. So there are, well, let me write this out a little more explicitly. We've got X1 is the 12 mice with the illness, and we have a sample size of 1,200. X2 is going to be the 8 mice with the illness and a sample size of 1,000. And from these values, we can compute PU hat is going to be 12 divided by 1,200, right? So 0.01. And PW hat is going to be 8 divided by 1,000, or 0.008. Okay, so there's our two P hat values. P bar, we're taking 12 plus 8, right? We're summing the two success numbers divided by the sum of the two sample sizes. And This works out to, if you want it in fraction form, 1 over 110 or 0.009 rounded. Okay. All right, there's that. And that gives us enough to compute our test statistic. So Z is equal to, and again, now we just have all the values. It's a complicated formula right here, but I'm just plugging everything in. So I have the PU hat 0.01 minus PW hat 0.008 minus the difference in our PU minus PW under the null hypothesis. The true population proportions we assume are equal, so that becomes a 0. And then we're in the denominator. We've got this under the square root. We take P bar. Where did P bar go? 0.009 or 1 over 110 times 1 minus 1 over 110 times 1 over the first sample size plus 1 over the second sample size. All of this is under the square root, and I'm getting a z-score of 0.492. Right? You've been working with normal distributions a lot. You might even have a guess already whether or not we've got enough evidence to reject the claim. But let's go ahead and do the computation. So with the z-score, we're doing a right-tailed test because our alternative hypothesis is that our difference proportion is greater than 0. Oops, so we're looking to the right. Dropped my pen. Hold on. Sorry about that. So our p-value is going to be equal to the probability of getting a z-score greater than, where'd you go? 0.492. And you can do this with any normal distribution calculator. I got 0.3114. This is greater than 0.05, which is our alpha. So we've shown that the p-value, I feel like after a while, my pen pad starts to break down and it just does a worse job, like it gets tired. Anyways, in any event, we've shown that our p-value is greater than our alpha, which would mean we reject the null hypothesis. We can also look at our critical value. This is the value, geometrically or graphically, maybe is a better word here, right? 0.05 area. You can use an inverse calculator to get that. This is above a z-score of 1.645. Our z-score of 0.492 is down below that somewhere, right? If the mean's about here, we're somewhere down there. So we're below the critical value in a right-tailed test, which, so I could say my test statistic, which is equal to 0.492, is less than 1.645, which is equal to which is our critical value. See, it starts to like break down after we've been going for a while. I think I'm writing the same way. Maybe I break down and my hand is not as controlled towards the end of the video as in the beginning. In any event, that's also gives us the same result, right? Which it should. Both cases tell us that we fail to reject H naught. In other words, we don't feel that we have enough evidence to dispute the claim that the proportions are equal. Right? It doesn't mean we're wrong. It just means we don't have enough evidence at this point, failing to reject. Okay, that is the test. So obviously, if it's below, you're doing a left-tail test. But once you get to that step, things are kind of looking like they did it for the hypothesis test with single proportions and single means. So, all right, that is it for this video. See you next time.